this case. So that's just this circle term transposed. What is the transpose of V transpose times A? A transpose V. A transpose V. Okay. What is the derivative with respect to me? Just the constraint itself, right? So again, we are essentially here. So the derivative is just the bracket. So AX minus B. And we know that the optimum, meaning when, by the way, here we have forgot X, right? So at the optimum, this has to be equal to 0. Okay. Now, how can we search for X star and V star? Imagine, I give you some matrix P, Q, A, B. And I ask you, give me the X star and V star. This is a system of linear equations. They are all linear in X and V. Okay. How do we solve a system of linear equations? If I have a system like m times z is equal to small m. And z, provided that m is invertible, that's just m inverse times m, right? So let us convert this problem into this form. What are the unknown variables? What is the vector z in our case? X star and V star. Okay? Now, this must be multiplied by some matrix, so these are essentially the multipliers of X star and V star. So what is the multiplier of X star in the first equation? B. What is the multiplier of V star in the first equation? X transpose. What is the multiplier of X transpose in the second equation? A. What is the multiplier of V transpose? 0. Okay. What about this 0? What is the size of this 0? How many rows and columns does this 0 matrix have? Because it's not a scalar 0. Okay, so here essentially A has n rows and n columns. Right? Because here we have two constraints in 3 variables. So this 0 has to have as many rows as A has rows, that means m rows. And it has to have as many columns as A transpose has columns. Meaning it's also m. Okay? But we still have the right hand side, the constant side. So what would be here in the first equation? There is a term here which is independent of x and v. And that's q.
Minus.
And we have to put it on the right hand side, so it's minus q. And here, okay. So these are the, and now this is that matrix capital M, which if it is invertible, it doesn't have to be invertible. But if the problem is kind of well posed, then it will be invertible. Okay. So this is essentially what then allows us to have a general kind of function or general implementation to which you just provide the parameters of the quadratic program, and then just by inverting this matrix and multiplying the inversion by this vector here, we can obtain not only the optimal solution, but we can also obtain the associated Lagrange multipliers. So here this is the amount of coal, amount of gas, and amount of oil that our company would need to purchase in order to satisfy the required heating capacity as well as to satisfy the volumetric constraint. And what we have seen here was just an application of the Lagrange method to this symbolic quadratic programming problem. And actually, this kind of procedure, I mean, it works for arbitrary constraints and arbitrary cost functions. But I should be careful here. It doesn't work always. And I want to show you a counterexample of when it doesn't work. So let us suppose we have a problem like this, and again, it's kind of a silly problem. Can you give me the optimal solution here? Just running mental optimization in your head. So x1 star must be equal to 1 because that's what the constraint says. that implies the second constraint that x2 must be 0. And then x3, what is the optimum of x3? That's also 0 because that's the minimum of x3. Oh, x3 squared. Okay, so that's the kind of the trivial solution. Now, what happens if we apply the Lagrange method now? It means we create the Lagrangian and we make the derivative. Okay, so that's the Lagrangian, that's just the cost function. This is the first constraint in the standard form, and this is the second constraint in the standard form. Now we take the gradient of the Lagrangian, which is like this. And we said, at the optimal point, the gradient goes away. The gradient is equal to 0 when we plug in the optimal solution. Okay? So let us plug back the optimal solution here. So essentially what we are saying is that the first line is just 1 plus μ1 plus 2μ2. Right? The second line is just 1 because x2 optimal is 0. So this term goes away. This is 0, this is 0, and this is 0 as well. Right? So essentially this is then the gradient at optimum. And Houston, we have a problem. It said at the optimum the gradient is equal to 0. But obviously, I mean here there is a constant in the gradient. Because of this constant, the gradient cannot be 0. Okay. So something went terribly wrong. What was it? Something went really, really wrong. And the thing which went wrong is that our problem is ill-posed. The reason here is that when we take the gradients of the original constraints, meaning no Lagrange business so far, just take the original constraints and take the gradients of these constraints. So the gradient of this constraint with respect to x1, x2, and x3 is trivially just this one, right? The gradient of this guy is 2x1 plus, the gradient at the optimum, so it's 2x1 plus 2x2 optimal plus 0 times x3. But we know that x2 optimal is 0. Okay? So the gradient of the constraints at the optimal solutions are what? What is suspicious about these two vectors? They have a property which ruins the whole, or ruins the application of the Lagrange method. They have a relation here. What is the relation between these two vectors? How do we call such a property that they satisfy? They are what?
If you multiply first by constant.
Okay, that's like the middle school. So let's try. They are linearly dependent. Right? Okay. So if the constraint, if the gradient of the constraints at the optimum are linearly dependent, the gradient of the Lagrangian cannot be 0 at the optimum, meaning the method cannot be used. And here we have the master theorem, the master theoretical result of the Lagrange method. It says that if we consider a problem of minimizing an objective function subject to a bunch of equality constraints, then exactly one of these statements is true. They cannot be true simultaneously. Either the gradients of the constraints at the optimal point are linearly dependent, meaning we cannot apply the method, or they are independent and we can apply the method. Basically, that's what it says. So here is what it really is. You start forming the gradient of the Lagrangian, and suddenly you end up with this case, and you start to wonder, did I make a mistake? I mean, wasn't the method supposed to work always? That always I should be able to solve this system? No, not always. There is an exception which says if the gradients of the constraints at the optimum are linearly independent, you cannot do anything. Okay? So don't be surprised when this case sometimes occurs. Okay? It can still be that you have done something wrong in the derivation of the gradient, but if you are convinced that the gradient is correct and you still see a problem, this is why the problem can occur. Okay? So that's kind of the exception we have to be aware of, which prohibits us to apply this method. So let me give you one more example of the Lagrange method, which will also illustrate the economic interpretation of those Lagrange multipliers. So far, we have considered the values of means as some abstract numbers. Actually, they have significant practical importance. And to illustrate that importance, let us consider a much simpler version of that network flow problem. We only have the starting node and the finishing node, so we are at the refinery. We have two pipelines through which we can supply the customer with oil. The customer requires exactly 100 tons of oil, and this is the price of shipping a particular amount of oil through each of the pipes. And we would like to find out the optimal allocation of oil to each of these pipelines, such that we minimize the shipping cost and we satisfy the quality constraint. Okay, so this is a trivial example. So we try to minimize x2 squared plus 1.5 times y squared, so this is the shipping cost, and we have a simple inequality constraint. This is a trivial example. Okay, so let's solve it using the Lagrange method. So step number one, convert these constraints into standard form. Step number two, form the Lagrangian by repeating the cost function plus the Lagrange multiplier times the left-hand side of the standard constraint. Then let us make the gradient, which is this one, put it to zero, equal to 0, and from that compute what are the optimal solutions. Okay, great. Now, please, one more thing is, usually in practice, we not only care about how much do we ship, but also how much did it cost to ship. That means we also do care about the value of the objective function at optimum. So here it essentially says at optimum it costs 6,000 monetary units to ship that amount of oil. Okay? And that's the cheapest we can achieve. Now remember this, and okay, let me also write it down. So when shipping 100 tons to the customer, that costs 6,000 euros whatever, and the corresponding me, and let me put an index 100 here, okay, to denote that that was for 100 tons, and the me was minus 120. Now, let me ask you the following question. What is the price of shipment when the customer now requires 110 tons? Now, if we want to know the exact answer, we need to solve the problem again. Right? So we again have to take the Lagrangian, which is a little bit different because the right-hand side is different. The gradient, therefore, will be different as well. Therefore, also the optimal solution will be different. Okay? And the cost is 7,260. Now look at the whiteboard. There is something strange about the relation between, so what we are saying is for 110 tons, the true price was 7,206. Can you see something strange here or suspicious? Essentially what we said was, we had a solution for 100 tons and that was 6,000. We increased the right-hand side of the constraints by 10, and the optimal solution increased to 7,260. What is the difference between these two numbers? 1,260. By how much did we increase the constraint? By 10. What was the Lagrange multiplier here? 120 minus 120. This is minus 1,200. Now, let's now forget about this one. Isn't it somehow interesting that by increasing the constraint, the value function increased roughly by the value of minus mi star times the delta of b, because that's what we have done. We have increased the right hand side of the constraint by 10. Okay, so the delta b here was 10. Right? So this increase here, so if I put it like this, the optimal value function for a change of b is roughly the value function for the original b, so let me put it like this, b plus delta, is equal roughly to this one plus, rather, minus mi transpose b times delta. Okay? And this says that these Lagrange multipliers, they have an economic interpretation. They say roughly by how much will the cost of the new problem change if I have solved an old problem and the new problem is just a slight modification of the previous problem. Essentially what happened here was that the Lagrange multiplier is kind of the derivative which says if I change the constraint, whether my cost will decrease or increase if I just operate closely. So if this would be b, the right hand side of the constraint, okay? That's the particular b that we have solved it for. Now we have said, let's increase the b to 110. Actually, because our Lagrange multiplier was negative, it essentially means not this one, but it essentially means something like this. Okay? So it was kind of a linear interpolation or rather extrapolation of the cost function for a change of the right hand side. And we can actually formalize this because it says that the new problem we can answer without solving it again. If you just want an indication, it will not be an exact indication, it will be an approximate indication. If we take the Lagrange multiplier for the original solution, then if we change the right hand side of the constraints to some delta, then the cost function will change roughly by minus the value of the Lagrange multiplier times the delta. Okay? So the minus here is important. Never forget the minus. Okay? And therefore, this Lagrange multiplier that gives us some kind of sensitivity of the optimal solution with respect to the changes in the right-hand side of the quality constraints here. And that's a very useful thing, because essentially solving one problem gives you an indication of how sensitive the problem is to changes in the constraints. It can be that the value of mi would be small. That means regardless of how much the customer requires more or less, you don't change the shipping cost. If you requires a large change and the value of mi is large, you know that also your cost of shipping will be very large. Essentially, now imagine that you are managers and you go to a meeting when you are discussing with the customer and you are negotiating the amount of oil that you can provide to him such that you are still profitable. All you need to essentially bring with you is this number. Because then if he says, I don't want 100, I want to make 120 tons being shipped. Immediately, 100 times 20 times the increment, in your head you can calculate roughly by how or what will be the solution of the optimization problem. Without needing a computer, without needing to write it on a piece of paper, nothing. So that's what's so nice about this Lagrange method. Not only it solves the problem, but it also gives you an economic interpretation of those Lagrange multipliers. And this sensitivity is very useful, and we will have more examples about this next time. So I will wrap it up here. I would like to thank you very much for your attention. If there are any questions,